All right, so picture the scenario. It's the absolute nightmare for anyone, working in back-end engineering. You're building this massive high-traffic e-commerce site. Maybe it's a flash sale or, I don't know, the launch of the year, the kind of thing marketing has been hyping for 6 months.
The classic Black Friday scenario, or tickets for a massive concert going on sale.
Exactly. The clock strikes 12 and users are just flooding in, thousands of them every single second. They're all hitting refresh, trying to load product pages, check inventory, add stuff to their carts. And here's the problem. Every single one of those page loads is a direct hit on your primary database.
Oh, yeah. I can already feel the stress levels rising just hearing you say that. That is a recipe for disaster.
The database is just chugging, the CPU is redlining, queries are piling up, and the whole system is threatening to just topple over. It's the classic too much of a good thing problem. You've got the users, but you don't have the infrastructure to greet them.
It's the bottleneck that kills success. If your database goes down, your business is effectively closed. You're losing money by the second, not to mention the reputation damage.
So today we're unpacking the solution to this nightmare. We are talking about the savior of the modern internet, distributed caching.
It really is the unsung hero of scalability. And I want to be clear right off the bat, this isn't just about making things load a millisecond faster for the user, though that's a nice side effect.
Right.
This is about survival. It's about protecting your database from being crushed by its own popularity.
And we aren't just going to define what a cache is. I think most of our listeners know, it stores stuff in memory to make it quick. The mission for this deep dive is to understand the architecture. How do you build a robust system using tools like Redis and Memcached? Because looking at the sources we have today, it seems like the tools are just the bricks. The architecture is the house.
That's the key distinction. Anyone can spin up a Redis instance in a Docker container. But designing the flow, understanding the trade-offs between consistency and speed, knowing when to use a write-through strategy versus a write-back strategy, that is where the actual engineering happens.
Okay, so let's start at the ground floor. Architecture 101. Where exactly does this distributed cache sit in the stack?
Think of it as a highly efficient bodyguard. It sits right between your application, your web server or microservice, and your database. When a user requests data, say, a product description for a new sneaker, the application doesn't go to the database immediately. It asks the cache first.
Like checking your pockets for your keys before running all the way back inside the house to find them.
Precisely. The cache stores frequently accessed data in memory, and that in-memory part is the critical piece. We're talking about RAM here, not a hard disk or an SSD.
I think it's worth quantifying that for a second. We hear memory is faster, but how much faster are we really talking? Is that noticeable?
Oh, it's orders of magnitude. Reading from a disk, even a fast SSD, is measured in milliseconds. Reading from RAM is measured in nanoseconds or microseconds.
Wow.
If we put it in human terms, if reading from RAM is like walking to your mailbox, reading from a disk is like flying to the other side of the world to pick up a letter.
Okay, that paints a picture. So by serving the data from the cache, you aren't just saving the database work, you're serving the user almost instantly.
Right. The database only has to do the heavy lifting when something is new or hasn't been cached yet, what we call a cache miss. If you design it right, 95%, maybe 99% of your traffic should never even touch the database.
Now, the sources for this deep dive highlight two big players in this space that seem to dominate the conversation: Redis and Memcached.
Those are the titans, yeah. If you're building a distributed cache today, you're likely using one of them.
So what's the difference? Or is it just a Coke versus Pepsi situation where they basically do the same thing?
It used to be a bit more like Coke versus Pepsi, but the gap has widened over the years. Memcached is the classic choice. It's a pure, high-performance, multi-threaded key value store. Very simple. String goes in, string comes out. It's incredible for simple object caching where you don't need anything fancy.
And Redis.
Redis is like Memcached with a PhD. It's single-threaded, which, well, it sounds like a downside, but actually avoids a lot of complexity around locking. And it supports complex data structures. You can store lists, sets, sorted sets, hashes. It's not just a cache, it's a data structure server.
But the sources make a strong point here. Redis and Memcached are just the engines. They're the storage. The design you build around them matters infinitely more than which one you pick.
Exactly. You can have the fastest Redis cluster in the world, but if your application logic for updating that cache is flawed, you're going to serve stale data, or worse, crash the system anyway.
So let's get into that application logic. The sources describe a menu of options for how we interact with the cache. It isn't just put data in, get data out. We have strategies like read through, write back. It sounds a bit like a tongue twister.
It does, but these strategies essentially define your consistency model. That's the fancy term for. Does the data in the cache match the data in the database?
Which seems like the answer should always be yes. Why would I ever want them to be different?
Well, in an ideal world, yes, you want them identical. But in distributed systems, we're always dealing with trade-offs between speed and accuracy. Let's look at the right path, because that's where things get tricky. Imagine you're updating a user profile. You change your email address.
Okay, straightforward enough. I type in the new email, I hit save.
Now, as the architect, you have a choice. Do you update the cache, the database, or both? And in what order?
I assume you'd want them both to be the same.
Ideally. And that leads us to the first strategy, write through. In this model, the application logic treats the cache and the database as a single unit. When you save that email, the application updates the cache and the database simultaneously, or at least in a tight sequence, before confirming to you that it's done.
So they're locked in step.
Yes. The big pro here is immediate consistency. You never have to worry that the cache says your email is old email at Gmail, and the database says new email at Gmail. They're always in sync. It's the safe bet.
That sounds like the default choice. But you mentioned trade-offs. What's the catch?
The catch is latency. Your application has to wait for 2 write operations to confirm success. You're writing to the cache, which is fast, and then the database, which is slow. The user sits there watching that little spinner spin until the database confirms the write.
So the user experience is only as fast as your slowest component.
Exactly. And if the database is under load, that write operation just hangs.
Okay, so if I need raw speed, say I'm building a real-time analytics dashboard or a gaming leaderboard where milliseconds count right through, might feel a bit sluggish, what's the alternative?
That would be write back, sometimes called write behind. This is for when performance is king.
How does that one work differently?
In write back, the application writes the data to the cache immediately, and then, well, it moves on. It returns success to the user instantly.
Doesn't wait for the database.
No, the database update happens asynchronously, basically, later. The cache itself, or maybe a background process, flushes those changes to the database periodically or after a short delay.
Oh, wow. So the user feels like it happened instantly. That must be incredibly snappy.
It enhances write performance significantly. It smooths out spikes in traffic because the database isn't getting hammered in real time. But, and this is where it gets really interesting and risky, what happens if the cache crashes 5 milliseconds after you wrote to it, but before it sent that data to the database?
The data is gone. The user thinks it's saved, but it never actually made it to permanent storage.
Poof! Vanished. That is the trade-off. You risk data loss for the sake of speed.
So you wouldn't want to use write back for, say, a bank transaction. I deposited $5,000 and the cache says, got it, then the cache dies.
And the bank has no record of it. Absolutely not.
Yes.
You never use write back for critical transactional data, but for a view counter on a video or a like count on a social media post, if you lose 5 likes during a crash, probably nobody's going to sue you.
That's a great distinction. It really comes down to the value of the data.
Exactly. Now, this whole idea of decoupling the write, of not waiting for the database, leads us into a really fascinating area the sources touched on, asynchronous architecture. If we're dealing with massive scale, like that nightmare scenario we started with, sometimes even direct caching isn't enough.
Right, because even with a cache, if you have 1 million people trying to write data at once, you can still overwhelm your systems.
Correct. When you have high write volumes, you need to completely decouple the ingestion of data from the processing of data. This is where we introduce a message queue, specifically something like Kafka.
Kafka pops up everywhere in these deep dives on system design. How does it fit into a caching strategy?
Think of Kafka as a giant, highly durable buffer. Instead of the application trying to write to the database or the cache directly, it just publishes a write event to the Kafka queue.
So the app just yells, hey, someone update this, and then walks away.
Essentially, yes. The app drops a message into the queue, which takes milliseconds, and immediately responds to the user. That ensures high availability and low latency on the front end.
But the data hasn't actually been changed yet in the database.
Not yet. Then you have a separate worker service, a completely different piece of software running in the background that's listening to that queue. It picks up the message and does the heavy lifting of updating the cache and the database at its own pace.
So if there's a massive spike in traffic, the queue just gets longer, but the site itself doesn't crash.
Exactly. It acts as a shock absorber. The worker processes the queue as fast as it can, but the user doesn't feel that weight.
But, and this is a big but, This introduces a concept the sources highlight called eventual consistency.
Eventual is a word that makes nervous system administrators start to sweat.
It sounds vague. Eventually, your money will show up.
It means that for a brief moment, usually milliseconds, but sometimes seconds, the data in the cache or the database might lag behind reality. If you update your profile via this async method and then immediately refresh the page, you might still see the old data for a split second until that worker processes the queue.
So again, if strong consistency is critical, like if I just transferred money or updated a medical record, I definitely shouldn't use this async method.
Correct. You stick to write through for that critical data. Async is for high-volume data where a split-second lag is acceptable to the business. It's a business decision as much as a technical one.
The sources also threw in a quick mention of Cassandra here.
Yeah, just a brief note that if you are using a NoSQL database like Cassandra in this mix, your schema design, how you structure the data, is going to drastically affect your write performance. It's just a reminder that the cache is part of an ecosystem. You can't design it in isolation from the database it protects.
So we have our basic caching, we have our async queues for the heavy lifting. Now let's get advanced. The sources mention that a cache isn't always just one big block of memory. It can be tiered.
This is a really sophisticated approach used by the big tech giants. Imagine you have different speeds of storage. You might use Memcached for your tier 1.
Why Memcached for tier 1?
Maybe because it's incredibly simple and fast, usually sitting right closest to the application, maybe even on the same server, but it might be small. Then, backing that up, you'd have a tier 2, which could be a much larger Redis instance.
So it's like a cache for your cache.
Exactly. Tier 1 holds the hot data, the viral video that everyone is watching right now. Tier 2 holds the warm data stuff that's accessed less frequently, but still needs to be faster than a full database lookup.
But wait, how does the application know where to look? That sounds complicated to manage. Do I check tier 1, then tier 2, then the DB? If I have to write code for all that, my code's going to be a mess.
You're spot on. You generally do not want the application logic handling that routing. That's messy and hard to maintain. Enter the traffic cop, Envoy.
Envoy. The sources describe this as a reverse proxy.
Yes. In a modern microservices architecture, Envoy sits in front of your caching layer. The application just talks to Envoy. It says, I need key XYZ. Envoy figures out where that request should go.
So Envoy is the brains of the operation.
It's the traffic manager. It handles load balancing, distributing requests across multiple cache servers so no single server catches fire. But it also does smart routing.
What does smart routing look like in practice?
Well, Envoy can inspect the request. It can say, oh, this is a video file request. Send it to this storage-heavy cache tier, or this is user session data. Send it to the high-speed tier 1. It abstracts all that complexity away from your application code.
That's incredibly powerful. The sources also mentioned testing capabilities with Envoy.
Right, because Envoy controls the flow, you can do things like canary deployments or A/B testing within your infrastructure.
Like sending a guinea pig into the mud.
Exactly. You can route, say, 1% of your traffic to a new experimental cache configuration to see if it works before you roll it out to everyone. If it fails, only 1% of users are annoyed, not 100%.
That seems much safer than just flipping a switch on a Friday afternoon and praying.
Much safer. And speaking of safety, we have to talk about circuit breakers.
I know this term from my fuse box at home. If I plug in too many heaters, the power cuts to save the house from burning down.
It's the same concept. In a distributed system, if a cache server starts failing, maybe it's overloaded or the hardware is dying, it starts responding very, very slowly.
And usually the app just keeps trying to hit it, waiting for a timeout.
Right. And while the app is waiting for that timeout, its own threads are tied up. Eventually, the app runs out of threads and crashes too. It's a cascading failure. One bad server takes down the whole application.
So the circuit breaker prevents this.
Yes. Envoy detects that the cache node is failing. It trips the circuit. It stops sending traffic to that bad node immediately and just returns an error or reroutes to a backup. It fails fast so the rest of the system can keep living.
Okay, so we've built this Ferrari of a caching system. We have tiers, proxies, queues, but you can't drive a Ferrari with your eyes closed. We need to talk about operational excellence.
Monitoring. You absolutely cannot run a distributed cache blindly. It is a black box unless you instrument it.
The tool of choice mentioned here is Prometheus.
Prometheus is the industry standard for this. It acts as the eyes of the system. You need real-time metrics. You need to know what's happening inside that cache right now.
What are the vital signs we should be checking?
First and foremost, cache hit rate. This is the big one. What percentage of requests are actually being served by the cache versus going to the database?
If that number is low, say 50%, your cache isn't really doing its job.
It means you're wasting money on RAM and your database is still suffering. You want that number in the high 90s. Then you have latency. How long does it take to get data? And error rates are requests failing.
There was one specific problem the sources highlighted that Prometheus helps detect: the hotkey problem.
Oh, the hotkey. This is a classic distributed system headache. Imagine you have a cache cluster with 10 servers. You think your load is spread evenly. But one of your items, say the page for the latest iPhone launch, is getting 99% of the traffic.
So one server in your cluster, the one holding that specific key, is getting hammered while the others are basically idle.
Exactly. It's uneven load distribution. That single node will crash. Prometheus can detect this spike in CPU or network traffic on that one node.
How do you fix that? If everyone wants the iPhone page, everyone wants the iPhone page.
You have to dynamically adjust. Once you identify a hotkey, you might replicate that specific key across all of your nodes. Or you might even cache it locally on the application server itself for a few seconds to stop hitting the shared cache entirely.
That leads us perfectly into scaling. When we get too big, how do we grow? The sources distinguish between scaling for reads and scaling for writes.
Right. It depends on your workload. If you're read-heavy, lots of people looking, not much changing, like a news site, you use read replicas.
Just making copies.
Yeah. You have one primary Redis node for writing and 5 or 10 replicas for reading. And you use something called consistent hashing to ensure that requests are distributed evenly across those replicas.
Consistent hashing is a term that sounds very academic.
It's actually brilliant. In normal hashing, if you add a new server, the math changes and all the data has to move to new locations. The cache gets flushed. With consistent hashing, if you add a node, only a tiny fraction of the keys need to move. It allows you to scale up and down without clearing your entire cache.
That is a huge insight. So you don't start from zero every time you add hardware.
Exactly. Now, if you're write heavy, lots of data coming in, replicas don't help because every replica has to copy every write. You'll just choke the network.
So what do you do then?
You need sharding. You break the cache up into chunks. So node A handles users A through M. Node B handles N through Z.
So you're splitting the write load across multiple servers.
Correct. Sharding gives you basically infinite horizontal scale for writes. But it adds complexity because now your application needs to know which shard holds the data.
It really is a multifaceted challenge. Listening to this, I realize it's not just plugging in a box.
No, not at all. It involves consistency models, tiered storage, protective measures like circuit breakers. It is intricate.
So what does this all mean for us? For the engineer listening who might be staring at a slow database right now?
It means that building a distributed cache is about designing flow. It's about understanding the journey of your data. It's not just about saving data somewhere. It's about ensuring that data is available instantly, reliably, and without killing your backend.
And if there's one thing to take away from all this, it sounds like it's don't ignore the dashboard.
Absolutely. Monitoring is paramount. Without tracking hit ratios and latency, caches fail silently. You won't know there's a problem until your database crashes and your phone starts ringing at 3 a.m.
We've covered how to get data in, how to keep it fast, and how to keep it safe. But here's a final provocative thought to leave you with.
We've talked about all the architecture for caching data, but there's an old joke in computer science.
Oh boy.
There are only two hard things in computer science: cache invalidation and naming things.
Cache invalidation.
Exactly. We spent this whole time talking about how to fill the cache, but determining exactly when that data is stale and needs to be kicked out, that is a whole different beast. Do you use a time to live, a TTL? Do you purge it manually? If you get it wrong, your users see old data.
It's easy to remember things, but it's hard to know when to forget them.
It is arguably much, much harder than anything we discussed today.
Something to mull over until our next deep dive. Thanks for listening.
Thank you.